So welcome to lecture 9 on the course Proof Complexity as a Computational Lens. We're talking about polynomial calculus. So we have some kind of field. We won't really talk too much about what the field is. So we're doing a quick recap. So I'm looking at the notation. We have some variables, and when I don't give them special names, I'll just write x with a vector notation, and that assumes that we have variables x1 up to xn, something like this. And we will tend to work with multilinear polynomials today. So this is the polynomial ring that polynomial calculus would normally work within, except we're just going to take away all higher powers right away. We're going to be in a multilinear setting. Recall that we also had, in polynomial calculus resolution, we had special variables xj bar, and we had axioms such that xj plus xj bar minus 1 had to be 0, meaning that we enforce that x and x bar are the negation of each other. We won't really use x bar from now on because we, as we'll probably recap shortly, we'll be focusing on proving degree lower bounds. And for degree lower bounds, it doesn't really matter if you have these extra variables or not. So what do we do? So what is a polynomial calculus derivation? Just to make absolutely sure we're on the same page. So a polynomial calculus derivation, pi, is a sequence of polynomials from some input set, fancy style p, such that for every pi is one of 4 things. Pi can be one of the multilinear input polynomials. And just to say that if we were not in a multilinear setting, pi could be a Boolean axiom, but those get modded away, so we won't really have these Boolean axioms. I'm just mentioning them for completeness. And then the fun part, and also, right, so pi could also be, as I mentioned, a complementarity axiom. We won't really care too much about these either, but let's just mention them for completeness, complementarity. And the fun part starts when we don't have axioms and we do derivation rules. There are 2 derivation rules in polynomial calculus. One is linear combination. So if I have 2 previously derived polynomials p and q, then I can derive 2 previously derived polynomial q and r. I don't know if I said something else. Then you can derive alpha q plus beta r, where alpha and beta now live in the fixed field that we're operating over. Or we can do multiplication. Multiplication, which just says, well, if I have a polynomial q, then I can derive mq for m any monomial. In fact, in the literature, usually we're a little bit more restricted in the theory literature, and we say just multiply by a single variable at a time. This doesn't make too much of a difference, except if you want to be really, really careful, it's not obviously the case that degree will stay exactly the same. This is kind of the proof system that makes most sense from an applied point of view with monomial multiplication. With variable multiplication, when you're simulating resolution, you're going to pick up an extra linear factor depending on the width. We're going to prove lower bounds for degree in this setting with variable multiplication. It's not so hard to show that the degree measures with monomial multiplication and variable multiplications are at most off by a factor 2 and maybe by less. I didn't have just the energy to think about it. For simplicity, we'll stick with this slightly simpler notion of multiplication today. And the refutation of a set of polynomials P is just the derivation of the multiplicative identity 1 in whatever field we're in. And we care about, for a derivation, we care about the size, which is the sum of the sizes of all the polynomials, which is what's the size of a polynomial. We expand it as a linear combination of monomials and then just count the monomials. So coefficients are for free. We just sum the total number of monomials in all polynomials in the derivation. That's the size. And the degree is just the maximum total degree of any polynomial that we see. Okay, and then we can do the obvious thing that once we fix a set of input polynomials, we can define the size of refuting this set of polynomials, which is the minimum size of any refutation, and similarly for the degree. And why we care about, we'll focus on degree exclusively from now on, because of what Impalazzo, Pudlak, and Skal proved. This holds even in the strongest possible setting, even if we take PCR, so polynomial calculus with resolution with dual variables in the multilinear setting, so the setting in which you get the smallest possible proofs, it still holds that the size of refuting a set of polynomials is exponential in the following quantity, exponentially in the degree of refuting P minus the initial degree, the max degree of any polynomial in P. Take this, square it, divide by the number of variables in P. So in particular, if I can get lower bounds, suppose that P, typically the kind of polynomials we will look at will have constant total degree input polynomials. And we're shooting to get this refutation degree linear in the number of variables, then we get n squared divided by n, and we'll get a truly exponential lower bound. So that's what we're shooting for. So it's fair to say probably that actually almost all, not quite, but almost all lower bounds for polynomial calculus go via this size degree relation. And note that this is a difference from resolution, where we also have lots of other proof techniques. But here, degree is almost the only game in town. So let us now recap. So now we wanted to prove degree lower bounds, and we started building this strange objects, these constraint variable incidence graphs. So let's, I'll try your patience a bit by recapping what these kind of objects were. And then basically what we'll try to do today is we'll recall what kind of bipartite graph representations we use to represent polynomials, and then see that if for a set of polynomials we can build a graph structure like this, then we automatically get a very strong degree lower bound. And we won't do all lower bounds. We'll do like several examples of polynomial calculus degree lower bounds. So this framework that we're going to see today, that we started looking at last time, and that we'll see again today, captures probably most of the polynomial calculus lower bounds in the literature. At least the lower bounds that don't depend on which particular field we're in. Okay, so that's what we're going to do. And then next lecture, the plan is, so today we're just going to take as a black box this claim that if we can build this graph structure, then we're home, and we'll study how to build these graph structures to make this a little bit more concrete, and maybe to sort of motivate ourselves a little bit if this whole framework seemed a little bit abstract. So we'll see today that actually if you can do this abstract thing, that you can do lots and lots of lower bounds, and therefore, motivated by this amazing discovery, next time we'll revisit the abstract framework and actually prove a lower bound in that setting, which is sort of a way of doing the lower bound proof once and for all, instead of, because the way it's done in the literature, for every lower bound you have basically, cranking the machinery again with slight twists. We won't do that. We'll do it only once. And then we'll see in a very general setting how you get lots of different lower bounds out of it. So what was this thing that we wanted to build? So we wanted to build a generalized clause variable or constraint variable incidence graph. It's a bipartite graph where we think of sets of polynomials living on the left. So the left side vertices are collections of polynomials. The right-hand side vertices are collections of variables. And once we've defined this, then the edges were obvious. We'll write it down in a second. But basically, once you just partition and divide up these sets, then any two vertices that share a variable on the left and the right, there's an edge between them. Okay, so let's recap this. So we have a set of polynomials, P, fancy style P, and we're just going to partition those. First, we singled out the set Q that somehow will not really take part in the lower bound, but sort of decides structural properties that we want our truth value assignments to have when we argue about the lower bound. And then we pick, say, M sets of polynomials that together with Q form a partition of the input polynomials P. And then we take the variables. So we have again, we have a set of polynomials, fancy style P, over a set of variables, fancy style V. So on the left, we divide P into, well, Q sort of goes away, and then we build the graph over the PI. On the right, we make that should have been a union. Let's see if I can draw a union symbol correctly. J goes from 1 to N, Bj. Now, as we will see today, it won't necessarily be the case that this is a partition. Okay? But we will care about that it's morally almost a partition. So we're going to look at all variables x, and we're going to see, okay, how many of these variable sets Vj contain x, and we're going to look at the size of all sets, such sets, and take the maximum. And this is like the maximum overlap of any variable. And we're going to require that this is a small constant. So it's almost a partition. And as we said, once you have this, we are going to define edges by just saying, well, from a set of clauses or polynomials here to a set of variables, we get an edge if the polynomials share variables with the variables. So is it clear that, like, once I just somehow, how are we going to do this partition, this division? Well, we'll need to think. That's part of what we need to do today. But once we've done it, like, we immediately get a graph just by this. Okay? And now we were interested in, we want edges to have nice properties. And so what did we refer to as a nice edge? I call them respectful. Last time, maybe we had a little bit too much terminology flying around. The paper calls them respectful. I think I'll call them today, maybe it's very tempting. I'll call the edge PC. Okay, it's a politically correct edge, or maybe it's a good edge. Last lecture it was a respectful edge. Whatever. Put your favorite, like, positive adjective here. So the edge will be good if the satisfier wins the following game. Played on this edge. So we're playing on PV, and satisfier starts by saying, here is my partial assignment row to the variables in V. And I'm writing top and bottom now because remember we're in an algebraic setting. So normally, actually, we kind of today think of true as being 0 and 1 as being false, but this is a little bit disturbing for us as computer scientists. So I'm sort of hiding this between these two symbols not to cause confusion, because also we will, of course, for when we have CNF inputs, we will overload the clauses and the polynomial representations of them, so it can be a little bit confusing. Anyway, satisfier commits to a partial truth value assignment. The adversary plays a total assignment alpha. I forgot to say something important about. So let me state, we said that rho has to be like a valid assignment with respect to Q. It has to either satisfy, like if it's affecting a polynomial little q in Q, then it has to satisfy. So another way of writing this, if you think about it, if I take Q and hit it with this restriction, I get a subset. Okay, meaning for every polynomial in here, either rho doesn't affect it at all, and then it's contained in here, or if rho does affect it, it makes it vanish. Okay, so this is the condition for rho. And then adversary plays an alpha, which is also valid. And since it's a total assignment, we can just say that, well, it should satisfy all of. I mean, a total assignment that satisfies this, well, there's no polynomials left, so it just has to satisfy everything. And then I say, okay, let's see what we have. I'll now define alpha prime of x to be the following. Well, for x in the set V, we take the satisfier choice. And for everything else, we take the adversary choice. Okay? And satisfier wins on this edge if alpha prime satisfies P, but it should also be still like a valid assignment as judged by Q. So we have to satisfy both P, which is the edge, and Q, which is this mysterious set that we removed from the beginning. Okay, and now we are at the point where we can state what we said last time. So the picture now that we have like a set of polynomials over here, and we have sets of variables over here. So here's like, I don't know, P1, P2, P3, P4, and V1, V2, V3, V4. And now we're going to get a lot of edges. Okay, so maybe we have these edges, these edges. I want one more, maybe V5. Something like this. And now I can just, for some of these edges, satisfier will win, and for some of it, satisfier will not win. Okay? But so suppose maybe these green edges are like the good edges. Say, maybe this is also a good edge. And the other edges are, let's say this is a bad edge, this is a bad edge, and this is a bad edge. And now I'm interested in unique good neighbors. Okay, so what are the unique good neighbors of this set? Well, first I look at this. First, let's pick out the unique neighbors. This is a unique neighbor, so it's a candidate. This is not a unique neighbor. This is not a unique neighbor. And actually, let's get one more bad edge, maybe. Suppose this is a bad edge also. This is still a unique neighbor. This is not a unique neighbor. Okay? Are you with me? So step one, when I want to see, is this like a good boundary expander? Let me first pick out the boundary. And now, once I'm in the boundary, obviously, like every guy over here is connected to the set here that I'm looking at the boundary for with some edge. And now I'm just going to say I'm only going to pick the good edge. Okay? So this was connected by a bad edge, so it goes away. This was connected by a good edge, this we keep. Note that this guy was connected by both the good edge and the bad edge, but it was V5 was filtered out in the first step. It's not in the boundary, right? Because it has two neighbors, and then I don't care about the quality of the edges. Okay, so you can take first generate the graph, and then just play this game on every edge. If satisfier wins the game, the edge is green. Otherwise, the edge is red. And then we're gonna pick like out the green expander. Okay? This making sense? So let's say that the boundary with respect to polynomial calculus, I'll probably drop this superscript after a while. If U prime is a subset of vertices on the left, then I say that the boundary are all the V's, capital V in fancy style V, such that two things hold. So V is in the standard boundary of U prime, and it is also connected with a good edge. And then I say that a PC expander is a graph such that whenever this set is not too large, this boundary is somewhat large. So now we're at the point where we can say, okay, this object that we built, a UV graph where U are these guys, fancy style U, V, fancy style V are these guys, Q is this guy. So such a graph is an S delta psi Q, let's call it a PC expander. I called it respectful expander last lecture. And these Q's are the same. It's an expander if whenever I take a left set of vertices, U prime, that is not too large, at most size S, and note that I'm measuring here the number of vertices. I'm not measuring the number of polynomials inside. I'm measuring just the number of clouds. Okay? If this is at most S, then I want the boundary to be at least delta times the size of U. And then if you really want the total power of what we did in the paper, you're actually going to carry along a small additive slack, because sometimes it's hard to get expansion for small sets. Pretty much from now onwards, nothing really fun happens with this slack. So let me sort of mentally, let me fix it to 0 for today. except maybe so okay, so this is an expander. So let me just give the statements. So we have two statements. First we have a general theorem and then a corollary, and we're going to prove the corollary next time because the theorem is kind of the same. So suppose that I have a PC expander like this, and suppose that the polynomials don't mention ridiculously many variables. Okay? But I will allow them to mention lots of variables. How should you think about these parameters? Delta you should think about as some positive constant. Xc we're going to fix to 0. S is going to be linear, ideally. Okay. So I say that, well, the number of variables is at most linear. Delta S minus 2 times the slack divided by 2 times the overlap. The overlap is also going to be a constant. So basically, this condition is basically I'm saying any single input polynomial should contain a total linear number of variables. That's like a very mild condition. Will be satisfied by any formula we can think of. So suppose this holds, and suppose we have found a way of looking at these polynomials so that we can build an S delta C Q PC expander. And suppose, furthermore, for all U prime that are not too large, suppose that I can prove that I take all polynomials in U prime and I have Q, and suppose I can prove that this is satisfiable, then we can prove that the degree in polynomial calculus of deriving contradiction from P, of refuting P, of deriving the field identity multiplicative identity 1 from P is strictly larger than delta S minus 2 times the slack divided by 2 times the overlap. Okay. And now a corollary, which is what we're going to prove and what we're going to use today, is, well, suppose the following. Suppose we have a standard expander. So the slack is 0. Then I don't need this condition. And also, obviously, the slack vanishes here. Then we just get outright the degree of refuting P is at least delta times S over 2 times the overlap. Okay. This requires a proof. Next time we're going to do this. Okay. What we want to do now is to just show how lots of the proof complexity literature on polynomial calculus can be recovered from this. So basically, because I don't know about you, but maybe this looks a little bit abstract. So we're now going to start looking at different CNF formulas, and we're going to build these objects. Okay? And what do we need to do? We will need to find a partition. We're going to have to argue expansion. We're going to have to argue about this game on the edges. And if we can do this, then we can just immediately apply the theorem, or rather actually we'll use the corollary for all the examples we do today and get a degree lower bound. And once we have, in fact, once we have a degree lower bounds, most of the time we will be able to plug in this. Okay, so maybe I actually want to save this somewhere. So let me note maybe over here that we know that the size of refuting P is exponential in degree of refuting P minus initial degree of p squared divided by number of variables. So whenever we can push this numerator to be linear, and then we'll pick up a square and divide it by the number of variables, and we're going to get something exponential. So again, just to be perfectly clear where we're going, basically what we're going to do today is we're just going to assume this corollary. Suppose I can build an expander with lots of good edges, no slack, then a degree lower bound holds. We're just going to accept this as true. We're going to prove it on Thursday. Today, we're going to build motivation for why this might be a worthwhile theorem to prove. Does this make sense? Any other questions so far? Okay. So let's now use this to prove some lower bounds. So our first observation are going to be random KCNF formulas. Okay. Basically, I'll do this a little bit quickly, but what's the idea? We'll have n variables. We'll have m clauses, which I'm going to pick as delta times n, where delta is the density. And I'm going to pick k clauses. Think of k as being constant for today. Now, it's not so hard to prove that if k, well, for any k actually, greater or equal to, if I have enough clauses, then there's a sharp threshold phenomenon. Like actually for two CNF formulas, we know exactly that the density 1 is critical. If when n goes to infinity, I have n variables and 0.999 times n clauses, and I sample this formula, with overwhelming probability it is satisfiable. If I have 1.0001 times n two clauses, with overwhelming probability as n goes to infinity, the formula is unsatisfiable. And people have even studied like how the width of this threshold shrinks with n. For k greater or equal to 3, we don't know that there is such a threshold. It is believed for 3CNF, there's a strong theoretical belief that there's a threshold somewhere around density 4.2. Okay, and there's this game that you can play. Like what we do know is that there is a lower bound below which you're with overwhelming probability satisfiable. I think it's like something like 3.5 for 3CNF formulas. So if I sample a 3CNF formula over n variables with 3.5 times n 3 clauses, then it will be satisfiable. Just will be satisfiable. And the upper bound, I think something like 4.5, definitely. As n goes to infinity, the formula will be unsatisfiable. For any k, there are such upper and lower bounds. Somewhat recent breakthrough in theory, what is it now, maybe 5 years ago or something, there are astronomically large k for which we actually know that there's a sharp threshold. Like, I don't know what k you have to pick, like a k like a billion or something like this. Bringing it all the way down to 3 is, I think, way beyond what we can do. But there's like a strong, there's definitely for any k, there's an upper and lower bound on the satisfiability threshold, and it's believed that this is time. So, and the point is that these randomly, so if I sample random KCNF formulas of high enough density, I will get unsatisfiable formulas. And this is one of the very few families, perhaps maybe the only family, that we believe to be hard for any proof system. Because somehow that why is a random KCNF formula hard? There is no really good reason. Interestingly, precisely for these reasons, proving lower bounds for random KCNF formulas is challenging precisely because these formulas don't have structure. So we have such lower bounds for resolution, and this was one of the early results. Remember, Haken was 85, and then Urquhart's 18 formulas 87, and then Patel and Zemredi 88 did random KCNFs. For polynomial calculus, it took until, well, in 1999, Bensasson and Impalazzo had lower bounds for polynomial calculus for all characteristics except characteristic 2. And then Alexnovich Razborov in 2003 proved exponential lower bounds for random KCNF formulas regardless of the characteristic of the field. In fact, Bensasson and Alexnovich and Razborov proved something slightly stronger. They proved that basically suppose that F is a KCNF formula such that the standard clause variable incidence graph, G of F, clauses on one side, variables on the other, edge if a variable appears in a clause. Remember, that's the clause variable incidence graph that we started with. If this is an S delta boundary expander as we defined before, then for any such formula, the degree of refuting F is strictly larger than delta S over 2. In particular, why will random KCNF formulas have boundary expanders? Well, if you just sample randomly a bipartite graph with left degree k, then this will be a boundary expander. If k is constant, n goes to infinity, and you have delta times n variable vertices on the left, n variables on the right, and you sample randomly, independently, k neighbors on the right of each guy on the left, it's an easy calculation that this will be a boundary expander. Okay. Now, if you think about how do you do when you sample a KCNF formula, well, if you first sample a KCNF formula and then look at the graph you get, that's just a complicated way of sampling a random graph. So in particular, a randomly sampled KCNF formula will have GF to be a random bipartite graph of left degree k. Any such graph with overwhelming probability is an S delta boundary expander. And if GF is an S delta boundary expander, then unconditionally the refutation degree has to be large. Okay, that's the claim. Is this clear? Okay, how would we prove this given what we have on the board? Well, we just have to build a graph, right? And since this is the first example, this is going to be really easy. I mean, so Q is going to be nothing. The set U is just going to be the clauses. So every clause will become its own vertex. Every variable becomes its own vertex on the right. What's the overlap? Well, 1. Right? Is this an expander? Well, I mean, I'm copying the graph, right? So it is an expander. What about the goodness of the edges, though? Okay, so very conveniently, I erased the game. So let's see if we can remember what it is. So again, the satisfier has to go first and play a row that satisfies the filtering set Q. That's pretty easy. And I'm allowed to, when we're playing on an edge, so we're going to be playing on an edge Cx for x that is a variable in the clause C. Okay? And I have to play a row that satisfies nothing. And I'm allowed to assign only this variable. And it seems like a good idea to satisfy the clause. Can I do this? Like, yes, I think we can all figure out how to do it. Okay. So in particular, if you're so lucky that your CNF formula F is already an expander when you look at the graph, then you get a degree lower bound for polynomial factor. Okay. Now, as we have argued before, for many formulas, this is not true. For pigeonhole principal formulas, they won't give us expanders. For taking formulas, also, if you look at the clause, they won't give us expanders. And that's when we're going to have to start doing some grouping of things. So the next example formula that we want to look at are going to be ordering principal formulas. So let me tell you what those are. So we have some set. And let me say that the set is V, and V has size n. I'm going to have variables x, u, v, which basically mean element u is smaller than element v with respect to some order, which we don't know, but these variables tell us. So now we're going to write down the claim that, in fact, we have a total order. Okay? How do we write down that we have a total order? Well, we say that if u is less than v, and if v is less than w, then u is less than w. Right? This is just saying if this is true, if u less than v and v less than w, then u less than w. This is transitivity. Then we want it to be an order, so it should be anti-symmetric. It's not the case that u is less than v and v is less than u. Let me say that I also want it to be total. So for every pair, either u is less than v or v is less than u. Okay, so far, so good. But now here's the amazing thing with this order. Fix v and consider all other u that are not in v. I claim that xuv, and do a big OR over xuv, I claim that this is true. Okay. So what is this formula saying? This formula is saying that I have a finite set of size n on which I have a total order, but apparently no element is minimal. Any v you think of, there's a u that is small. Okay. These formulas were studied, some version of this formula was studied already back in the 80s and was conjectured to be hard for resolution by Krishnamurti. Interesting is, we'll see in a future lecture, they're actually easy for resolution. And this is a result by Stallmark, which is far from obvious. It's a very nifty proof, you can think of it. And now we want to use this to show that this result is essentially tight. Okay. So note that the number of variables here is n squared. So if I could prove like a degree n lower bound, then I would get a square root degree lower bound, and then I square root squared is like n divided by n, and I get nothing. And this would, and since these formulas would be easy for resolution, this kind of says that yes, this has to be true. If you have only square root lower bound here, then it doesn't imply anything. It's sort of, that shows that you cannot really improve this to what we had for tree-like resolution. There's only one problem, yes?
What was the last clause encoding?
This clause is encoding that V is not a minimal element.
Oh, I see. Okay.
Okay. But the problem with this clause is it's pretty wide.
Right.
So already we're going to pick up a linear factor here. So this is a little bit annoying. And now there are different ways around this. What we are going to do, we're going to fix a graph GV, and we're going to restrict the witness and say, well, actually, the fact that V is not minimal is witnessed by a neighbor of V with respect to this graph. And we're going to pick a V to have bounded degree. Okay, so now we get a KCNF form. And now the thing makes sense. So now we say that a standard graph is a, well, let's say that it's a non-bipartite boundary expander. If the following holds, if for all vertex set V, boundary expander wants parameters S and delta, V is not too large, V prime, it's of size at most S. For any such set, it should hold that the boundary of V prime is at least delta times V prime. And now I just have to tell you, what do I mean by the boundary here? Well, the boundary here is just going to be, I'm going to look at all vertices that are unique neighbors. So the neighbors of V intersect V prime is a unique neighbor. And then I'm also going to say that I'm only interested in things that are outside of V prime. So let miss the, you can see that for a bipartite expander, this sort of automatically holds, right? Because the edges are on the other side, as long as I'm looking at left expansion. Okay. And now if you sample a random regular graph and you do your calculations, you'll get like a 5 regular graph or something, you'll get an expander according to this notion. Okay. And now what we're going to say is like, pick any graph like this that is an expander, look at this formula. This has somewhat high degree, namely a result by Galesi and Lauria from 2010. They proved that the degree of, let me call this formula the graph ordering principle over G. So if G is an S delta non-bipartite boundary expander, we get a degree lower bound delta S over 4. And again, I think I said this already, like, for instance, if you pick a random 5 regular graph and you do the calculations, then asymptotically or most surely this will be an expander. Okay. Suppose I can show this, then again, how many variables do we have in this graph? So this is going to be, we're going to have, so again, okay, so maybe I should write this, a random, because I'm going to need it, random 5 regular G is a big omega of n, some delta greater than 0 boundary expander. The number of variables, as we talked about in this graph ordering principle formula, G is n squared. Okay? And it will be a 5CNF formula. Okay? So the lower bound here is going to be the degree lower bound n, because delta is going to be a positive constant, S is going to be big omega of n. So this is going to be linear in n. Minus 5, still linear in n. Squared, this is going to be n squared. The number of variables is n squared. And we'll see in a future lecture that these formulas have short, even resolution reputations that are short. So definitely polynomial calculus resolution reputations that are short. So this tells you that you could not really expect to like improve this to, for instance, maybe I need something only 1.5 or something like this. This kind of shows that this expression is very nearly tight. Am I making sense?
Okay.
right? Because note that for tree-like resolution, any non-trivial width lower bound, you immediately pick it up in the exponent, right? If I had for a CNF formula, I could prove a super logarithmic with lower bounds, then immediately for tree-like resolution, I got a super polynomial tree-like resolution length lower bound. But this tells you that for polynomial calculus and for resolution, you cannot hope to get anything. This is somehow, I mean, of course, you can maybe get different types of expression, but on this form, you cannot really hope for anything. Okay. But we need to build, I mean, we need to prove this. So how are we going to prove this? So let's see. So this was transitivity. This was the symmetry. This is totality. And these axioms are the non-minimality. Okay? Minimality. So all we need to do now is just to build a graph and argue that it's an expander and that it has good edge. Okay, how are we going to do this? So the filtering set is basically, we're going to argue about orders. So let's throw in transitivity, asymmetry, and totality. Which is sort of saying that when we're going to argue about truth value assignments, they are not crazy, they will somehow encode orders. So we're going to argue about actually somehow ordering these elements U and V. U are going to be singleton sets with the non-minimality axioms. Let's say PV is the axiom saying that V is not the minimal. The division of the variables I'm going to do is for every vertex V in the graph, I'm going to define a set V sub V. And this is going to be the following. V sub V contains all the variables X, U, W such that either U is V or W is V.
U is 0. Is this?
So I'm going to, V sub V contains all variables X, U, V. For these are ranging over all possible vertices, except that either U is fixed to V and W is anything, or W is fixed to V and U is anything. Make sense? What overlap do we have here? Yeah,
Two.
Two.
Because sort of the variable mentions two, like the index of a variable mentions two vertices, like two things.
Yeah.
Two vertices.
So let's just look at, you know, XAB. It will appear in VA and in VB, right? So the overlap is 2, and then you can guess that we were kind of expecting to get, we were expecting to get 2 times the overlap here. So we're in good shape. 2 times 2 is 4. Okay. So now we're done. So all I need to prove to you now is, in fact, I claim, okay. We're going to claim that all edges from PV to VW are good, or politically correct, or good, or PC good, whatever. Okay. If this is an edge, there are two cases. Either V is a neighbor, W is a neighbor of V, or W is V itself. And now, let's look at W is a neighbor. Then I have to make, okay, what can I do? W is a neighbor. I have to make this axiom happy. Okay, so what do I have to? I have to argue that V is not the smallest element, and I can assign variables related to W. Like all variables related to W I can assign. What would I do?
Say that W is less than.
Say W is the smallest. Right?
It's small, yeah.
Let's say W is, let's go big. W is the smallest among all, right, in fact. So I'm going to say that rho W U is true, and rho X U W is false. I mean, this once I have committed to this. Note that. Okay, so note that for every variable xab, I will always have xba also. And once I have committed to truth value to this guy, I better commit to the opposite truth value to the other guy, because otherwise I'll screw up my filter. Okay. Now I claim it's clear now that we're satisfying the non-linearity axiom. In particular, xwv is true. Okay. What about the filtering set? Well, these two guys are fine, because I'm at any, like, either I assign none of these, and then we're not touching this, or if I assign xuv, then I also assign xvu, just by the structure of how vv looks, right? Whenever I assign xab, I will also have to assign xba, because they come in pairs in the set. Are you buying this? But note that I'm making sure that exactly in every pair, one is true and one is false. Okay, but then I don't have to worry about these. That clear? Okay. So now let's just think about. Let's think about the. Okay, so that what? So we claim that a symmetry Q, a symmetry and totality are clearly okay. What about transitivity? So suppose we have x a comma b, not x a b, or not x b c, or x a c. So note what I'm worried about now is that xab being set to true, or xbc being set to true, or xac being set to false. Other assignments would be good. Okay, so let's look at, copy it over here maybe. Let's just do a case analysis. So we have x ab or x bc, not or x ac. Okay. So and let's see what rho does. So here's the variable. Here's rho. Suppose that xac is true. Well, then we're happy. Is there a question? Right? Okay. What if XAC is false? Well, if XAC is false, that means that once the only way a variable is set to false in this case is that C is W. So then anything C will be set to false. In particular, also BC is set to false. So the clause vanishes. Okay, good. So now you say, let's look at XAB. If XAB is true, then we're a little bit worried. But if XAB is true, then we know that A is W. So anything with A to the left is true. So in that case, XAC is also true, and we're fine. And XAB false is clearly okay. Okay, and now we just have to see, we can do also XBC. XBC being false is okay. XBC being true. Again, XBC being true means that B is, what is B? I guess it's W. And now we want to say, then in particular, anything with W here is false. So then XAB is false. And we're good. Are you buying this? Okay. So now, okay, so then we have the other case. What if the other case, if W is equal to V, then what should I do? So now we have an edge from PV to VV. I have to make PV happy. What should I do? PV claims that the V is not the minimal element, and I can assign any variable containing V either here or here.
So it's V to be the maximum, right?
Exactly, right? So let's do UV to be true and VU be false. And I'll do the same kind of case analysis. Okay. So the final thing is, but is this bipartite graph a good expander? If G is a good expander. And the answer is yes, because basically, so now I know that all edges are good. So suppose now we have a vertex at V prime in the graph G, this graph, the graph over which we're generating the formula. So we're interested in the unique neighbors of all, so we're taking the union over all V primes in V prime of all these PVs. And I claim that in particular, suppose that some W prime is a unique neighbor in the original graph of lowercase v prime. Okay, well, if W is the only guy in V prime that is a neighbor of, like if V prime, W prime is a unique neighbor pair inside V, then definitely there will be no other PV that gets an edge to that. So okay, I'm not saying this really well. Let me try to write it down. I'm claiming that this containment clearly holds. that in this boundary, clearly I get VW for all W's that are actually in the boundary of V prime with respect to the original graph G. Okay, but this means that our UVQ graph has at least as good boundary expansion as the non-bipartite graph G.
And this is really good what Kalesi and Lauri are doing under the hood.
Okay, good. So I almost forgot. So no, they're doing, so they have a slight, okay. So I think if you do the calculations, we can get this to work for 5 CNF formulas because random 5 regular graphs are good enough. Random 3 regular graphs are not good enough. So come to think of it, I guess you could probably do a 3 regular explicit expander construction, probably, but I don't think they use explicit construction. They use a random argument. Their expansion, they don't require the expansion to be outside of V prime. And therefore, they can get, I think, okay, I'm a little bit out on thin ice now, but I think they have the same random argument, but they have a more generous boundary, so they can get it for 3 CNF formulas. And we only, in this setting, you get it only for 5 CNF formulas. If you do it randomly, I think we could probably do it maybe for 3 CNFs if we plug in explicit graph constructions. I didn't think about this.
Okay.
So, but you could say that that's kind of almost what Kalesi and Lauri, it's sort of morally the same thing. So they're tweaking the nuts and bolts a little bit differently so they get slightly better parameters. But under the hood, yes, this is kind of what's happening. Okay. Good. So what I would like to do after the break is to say, okay, what can we now do for different styles of pigeonhole principal formulas? Okay, so we're going to have a break, but after break, we're going to talk about pigeonhole principal formulas. Now you realize again, if we just take the pigeonhole principal formula as is, we can never hope for, well, firstly, the axioms will have linear width, the pigeon axioms, for instance. And also the number of variables is quadratic. So we lose on, we can never expect to get anything really good here. And we're dividing by n squared anyway. So we need to fix this somehow. And the way we're going to fix it is we're going to take the pigeonhole principal formulas and define them over bounded degree bipartite graphs. And if you think about it, when you do this, you can take the standard pigeonhole principal formula that we talked about before, hit it with a restriction, namely the restriction that just zeroes out the variables corresponding to all the edges that are not in our graph. Okay. Now, both resolution and polynomial calculus are well behaved under such restrictions. So if I start out that I have an amazing polynomial calculus proof for a pigeonhole principal formula, I hit it with a restriction, I hit the proof with the restriction, I get a proof for the restricted formula, and get most the same size. Okay. Which means that if I can prove size lower bounds for the graph pigeonhole principal formula, then obviously that gives me lower bounds for the original formula. And once I'm down to pigeonhole principal formulas where every pigeon can only fly to a constant number of holes, my number of variables will be linear, which takes care of the denominator. And the initial degree will now be constant, namely the pigeon axioms to say every pigeon can fly to at most k holes, where we can pick k to be 5 or something. Okay, so then this degree is going to be constant, and now we're in business if we can prove linear degree lower bounds. And we are going to be able to prove linear degree lower bounds if we can build objects like this. Yep. Which we're going to do after the break. Questions before we take a break? Then let's take a 10-minute break. So we're back after the break. We're going to talk about graph pigeonhole principal formulas. And let's just say, so one thing that I said, for any type of pigeonhole principal formula, so how do you go from kn plus 1 n, the complete bipartite graph with n plus 1 vertices on the left, n vertices on the right, to a bipartite graph G U union V E? Well, as we said, you just take rho, and it's going to do the following. If UV is not an edge in E, then, then we're going to set UV to 0, and otherwise we leave it unchanged. Okay? Then it's kind of clear that any type of pigeonhole principal formula, and we'll see a few flavors with n plus 1 pigeons and holes, you hit it with this, let's call it rho G. This will then give us the same kind of pigeonhole principal formula, but we'll write it over the graph G. Does this make sense? And clearly what I'm saying is if we prove exponential lower bounds over here, then clearly those exponential lower bounds apply over here. Okay? So it is not too hard to do lower bounds for vanilla pigeonhole. So what different versions of pigeonhole principal formulas do we have in the graph setting? For every pigeon U, it flies to one of the V's that is a neighbor. Note that this is what we got down to constant width by looking at the constant left degree bipartite graph. And then we say for any pigeon U and two holes V and V prime, for any hole V and two pigeons U and U prime that could both fly to D, they're not both doing it. Okay, that's a whole axiom. A functionality axiom says that pigeon U is not allowed to hold two holes V and V prime. That's not fair. Every pigeon gets only one hole. And then onto axiom says that every hole V should get one of its pigeons. And now if you want to be careful, then I probably, we want to, in order for this theorem to be meaningful, if we're going to look at onto pigeonhole formulas, then we want to have bounded degree on both the left and the right. Okay, so the vanilla pigeonhole principle contains this pigeon axioms and hole axioms. The onto pigeonhole principle is if I throw in onto axioms also. The functional pigeonhole principle is if I throw in pigeonhole and functionality axioms. And then finally, the onto functional pigeonhole principle is I throw in everything. Okay, and if you think about it, the onto functional pigeonhole principle is just saying that there's a perfect matching in the graph. Now, as I said during previous lecture, didn't prove, but it's not so hard to prove, for any field, a bipartite graph with n plus 1 vertices on the left and vertices on the right, onto functional pigeonhole principle or perfect matching is easy because you just count modulo the field characteristic and you see that the number of pigeons and the number of holes don't match. But so you have to remove either onto or functionality, and what happens when you remove one? So it's easy, or already Alexnovich and Sporo, I don't think they stated it for onto pigeonhole principle, but you can basically do the same proof that they did, expressed in our language. Again, to get an onto phi lower bound delta S over 2 for an S delta boundary expander without isolated vertices on the right, we just need to build a graph. And the proof sketch, I'm not going to do this super carefully. The proof sketch is just going to be, well, let Q be hole plus onto axioms. Let U be singleton pigeon axioms. Every pigeon axiom just gets its own vertex. And the way I divide up the variables is that xuv is going to be, so vv are all the XUV such that U is a neighbor of V, this fixed V. So basically, I just partition the all variables speaking about a particular hole just goes into that hole. And now I just claim that everything works. So this graph is going to be isomorphic. The UVQ graph is going to be isomorphic to this graph, so it will inherit the same expansion parameters. All the edges are good because basically you have what I need to play is I'm playing on VV and I need to make pigeon U happy, that is a neighbor. What will I do? Well, I just place pigeon U in my hole and I say no other pigeon goes into that hole. And I just verify that this works. I'm not going to say much more. So the interesting thing is, suppose I now remove the onto axioms. Let's throw in the functionality axioms. Can I do this? And the answer is no, because one way of seeing it is that suppose I send U to my hole V. I have to do that, right? If I'm playing on PU VV, I have to send pigeon U to pigeon V. Of course, as an adversary, I would send pigeon U somewhere else as well. Okay. And then you can start thinking about the problem. What happens if I can only talk about the variables for hole V, but I have to satisfy a lot of functionality axioms? As soon as I send U to V, I'm hitting but missing all functionality axioms for U. And suddenly I get a lot of clauses of size 1 saying, no, U is not allowed to go there, not allowed to go there, not allowed to go there. So I'm not being respectful. This is not a good assignment. Is this making sense? Okay. So what are we going to do about this? So what we can prove is the following. So suppose that G is a bipartite graph. It is a bipartite S delta expander. Bipartite S delta expander. Suppose that the left degree is at most D. Okay, so every pigeon can fly to at most D holes. Then what we can prove is that the functional pigeonhole principle, PHP, over this graph requires to refute degree at least delta S over 2 times D, which will make into a small hole. Okay. And then, so we did this back in 2015 is the conference version, so it's not quite that new, but okay. So, okay, how do we do this? Well, we're going to build a UVQ graph. You can sort of already guess that we're going to have overlap again, right? This is sort of this is the overlap parameter. So what are we going to do? So Q are going to be whole plus functionality axioms. As before, U are going to be singleton pigeon axioms. As before, we're going to somehow pick out one variable set per hole. But now, the way I'm going to define the variables for the hole V is as follows. all variables xu prime v prime that I can obtain in the following way. First, let me start with v. Let me look at what holes u prime can fly into v. Then, for all such u prime, let v prime be a neighbor of u prime. Okay, so I start in v, and any pigeonhole pair that I can reach with two hops is going to be in this set. Okay? Does this make sense, the definition? So I start with v, consider any u prime that can fly to v, and then consider any hole v prime any such pigeon could fly to. We can already see from the theorem statement that the overlap should be at most d. Why is this? Well, because xuv only appears in v prime if v prime is a neighbor of u. And how many such guys are there? At most d. Okay. Now I claim that the graph G here and the UVQ graph is the same. And the way to do this is to just check, well, if UV is an edge in G, then clearly it will be an edge in here. But also in the other direction, if you go in the other direction, the only way you can have an edge from PU to VV is that actually is exactly that V is in the neighborhood of U. I'm sort of just spreading out all the neighbors. Okay, so the only remaining thing I need to do now is to just argue why all the neighbors are good. Or why all the edges are good. Okay. Need to prove that all edges are PC good. Okay. So consider PU. What is that? That's a big OR of W in the neighborhood of U such that U flies maybe to W. Right? This is what PU looks like, a singleton clause. And then we have a VV, capital V, lowercase v, for a lowercase v that is in the neighborhood of U. Okay? That is what it means for P, U, V, V to be an edge. Okay, so for this edge, I need to define a row UV that assigns values to variables x, u prime, v prime. And let's see what can we do. Well, we have to make pigeon U happy. So I'm going to set this to true if U prime is equal to U and V prime is equal to V. Right? Then I'm definitely taking care of U. Now I need to worry about whole axioms and above all about functionality axioms. So the way I'm going to deal with this is just say everything else is false. Okay, or otherwise, everything else is just set to false. In particular, there are lots of other pigeons here around, like, look at all the other neighbors of V. They are, in fact, in this set, right? This set contains all the neighboring pigeons of V. All of them suddenly get to know that they have no holes to fly to. I just kill all of them. But we don't care because we're playing on this edge. I don't, like, if you falsify the rest of the formula, sorry, I mean, we're just going to evaluate this single false. That's the rules. We set the rules before. Okay, so now the whole axiom are clearly satisfied. Like all whole axioms, I'm talking about VV are talking about all holes to which pigeons that can fly into U can also fly to. For all of those holes, they get either no pigeon, or in the case of V itself, it gets one pigeon. Okay. So for whole axioms, most whole axioms will have both of these literals false, or for V we have XUV true, and for all other U prime it's false. So the whole axioms are okay. And now, for the functionality axioms, you just verify this and you realize that for the functionality axioms, I'm worried about U again, right? Because I sent U to V. So I have to make sure that U does not fly to any other hole. But this I know by the way I constructed this. Because I know that all other holes that U could fly to are actually in this set. And I'm setting all of them to false. Okay, so I'm definitely taking care of the functionality axiom for the pigeon U. What about the other pigeons? Well, any other variables that I'm setting them to false. So if I touch any other functionality axioms, I'm setting the literal to false. So we're good. And now this in particular proves that for the full functional pigeonhole principle over the complete bipartite graph, n plus 1 pigeons, n holes, you also get an exponential lower bound for polynomial calculus by this restriction argument. Okay, now I want to talk questions about this, because this was our last formal proof for today. So now what I hope is to have convinced you that there are also some other lower bounds that I'm not doing that you will find in the Mikša and Nordström paper, and they all go, so all of the lower bounds go by, again, just build this UVQ graph object and then play on the edges and then you're good. So we really reduce everything to just, can I build a graph like this where I can play the game on the edges? How does that give me a polynomial calculus lower bound? Well, if I can do that argument once, then I will get everything we did today. That hopefully serves as motivation why this is a meaningful technical theorem to prove. Okay. Questions on this? Because now I'm going to talk about, in the time that remains, I want to talk a little bit about where do we go beyond this? Because there are tons of nice open problems for polynomial calculus. Polynomial calculus is a proof system that is close to resolution in the sense that there are a lot of parallel results, and many things that we know hold for resolution can also be shown to hold for polynomial calculus, but proving them for polynomial calculus is much more challenging. So it's like a test bed for, there are lots and lots of results where you can say this holds for resolution and it seems like it should probably be true in general. Can we at least carry it to the next step? Then there are some things that fail for polynomial calculus, and then it's interesting to figure out why. Okay? So I want to discuss now some open problems and some not so open problems. Before I do this, is there any questions about these UVQ graphs? This final functional pigeonhole principle, I did maybe the overlap a little bit quickly. The fact that rho is good, maybe also I did a little bit quickly. The way I know how to do this is you really just go over the clauses one by one and just check. But basically, as I said, so functionality is fine because I built the VV set so that whatever XUV I set to true, I have control over all the other holes that pigeon can go to, and I falsify them. That's the difference. Now I pay a little bit for it, right? That's where I pay the overlap D. But that's the functionality axioms, and then the whole axioms, they were kind of fine already before. And clearly, if I'm sending for PU, if I'm sending it to a hole, then it will be happy. So that's all there is. Anything else that would be helpful to say about this before we move on to some open and not so open questions? Okay, open questions or not so open questions. Graph coloring, so you can write down formulas saying that I have a graph and it is K colorable for K3 or some larger constant. We have strong lower bounds for resolution. Can you do it in polynomial calculus also? The answer is yes. And this is what we're going to talk about probably next Tuesday. I don't know how to do it with this framework though. This is the one lower bound that I should say there are some other lower bounds in the literature, some other Galicia-Lauria papers that don't quite fit this. But this is sort of, you can take our framework, and if you're willing to make it ever so slightly more complicated, then you can capture this also. For the graph coloring, I fundamentally don't know how to do it. There's a worst case lower bound by myself and Massimo Lauria from 2017, where we just basically use a reduction from the functional pigeonhole principle and get worst case lower bound for coloring. Average case lower bounds, I don't know how to do in this way. So coloring, yes, but not with this technique. What about clique or vertex cover? Well, that is the example of, there's this beam in Pagliazzo Sabarval paper from 2007. There are resolution lower bounds. We don't know how to translate these to polynomial calculus. There are a number of Ramsey theory style problems. Like you're saying, pick a graph. So again, a Ramsey graph is something like with parameters such and such that it either has a clique of this size or it has an independent set of this size. And now you can basically write down parameters that, okay, no, but I have a graph over so and so many variables that doesn't have a clique of this size and also not an independent set of this size, and where the Ramsey theory parameter just says that, well, sorry, this is not possible. And now we have an unsatisfiable formula. We have lower bounds for those types of problems for resolution. And there are a number of papers. There are papers by Carlucci, Galicia and Lauria, 2016. There's a paper by Lauria, Pudlak, Kredl and Papen. 2017, there is an older paper by Pudlak from 2012, where different types of Ramsey-style problems, we have resolution lower bounds. Can we do them for polynomial calculus? I don't know. One interesting problem is degree lower bounds for dense linear order formulas. So we looked at the linear ordering principle just says that I have a finite order, but it has no minimal element. The dense linear ordering principle encodes the statement that I have a finite order and that it is dense. Okay, so if x is smaller than u, then there is a z in between x and u, x and y. So if x is smaller than y, then there's a z in between. And for any such pair, then you can drill deeper and say, oh, what about x and z? Well, there's something in between there as well. And the dense linear order says that this never stops. These formulas were studied by Atselias and Dalmau. And they proved resolution with lower bounds. Interestingly, we cannot quite get polynomial calculus degree lower bounds. These are also another formula family that shows that the Impalazzo, Pudlak, Skal, and Bensason-Wigderson size degree / width relations are essentially tight. We don't know how to get this lower bound for polynomial calculus. And it's interesting why we can do it for resolution and not for polynomial calculus. I think this would be nice to work out. The weak pigeonhole principle formulas for, say, n squared pigeons or more. They're saying m pigeons can fly into n holes. You can do it, functional. You can do it onto, but pick the number of pigeons to be at least n squared. Now, the degree lower bound and also for resolution, the width lower bound argument fail. Because now the number of variables will be so large, even in a bounded degree setting, that even if you, the degree lower bound is still true, but it doesn't buy you anything. You don't get size lower bounds. For resolution, there are papers by Raz and Razborov from the early noughties that showed exponential lower bounds anyway. These can even be translated to bounded degree graphs if you have good enough expansion. And this is by Susanna de Rezende, myself, and Risa and Sokolov. Actually, I think the journal version from this year. For polynomial calculus, I'm not aware that we have anything. Again, it would be somewhat surprising if the pigeonhole principle with n squared pigeons and n holes were somehow easy for polynomial calculus. But it's just, we just can't get any polynomial calculus lower bounds because, again, we basically have only degree, and degree won't give you anything in this set. What about field-dependent lower bounds? So Alekhnovich-Razborov actually has, in their paper that we started, the Alekhnovich-Razborov 2003 paper, what we have used so far and will develop more next time is kind of a special case in that paper. And they also have another version of their technique that works where you start looking at what exactly the field is. What happens with that technique, though, it kind of breaks when you want to start working with this clustering and filtering set Q and stuff. So the Alekhnovich-Razborov method will work sometimes for field-dependent lower bounds, but only looking at the original graph, essentially. And it would be interesting to somehow look at Alekhnovich-Razborov and see, can you somehow combine it with what we have been talking about and get lower bounds that that where you can build this, you can build a structure that corresponds to the combinatorial principle and yet get lower bounds that depend on the field. Because one thing that it's worth noting that whatever we have done, we never talked about the field, any properties of the field. So the technique that we're talking about now, either it works for any field or it doesn't, right? For Zetin, for instance, this is crashes and burns because we don't have Zetin lower bounds for GF2. Now, it so happens that Zetin is exponentially hard for GF3. We are not able to prove it with these techniques. You need other techniques. The one good way I know how to prove that is this trick we talked about, that you do an affine translation to ±1. And then in that setting for Zetin, it becomes easier to argue about degree lower bounds. And now you prove a strong degree lower bound, and then you can translate back. Because degree lower bound doesn't change because of this affine translation. But we cannot do it in this setting, not that I know. Two final interesting problems are, what about onto functional pigeonhole principles or perfect matching with n holes and m pigeons where m is n plus p to the d, where p is the characteristic of the field we're in. Okay. Remember, why is n plus 1 pigeons and n holes easy? Well, because we just count. And in any field, n and n plus 1 are different. But in a field of characteristic p, n and n plus p to the d are not different. Now, it turns out for Nullstellensatz, we know that you have degree lower bounds that actually scale with the exponent d here. For Nullstellensatz, you have degree lower bound between 2 to the d and p to the d. Okay, we don't have anything like this for polynomial calculus. Yes?
Why is only, like, why are prime powers more interesting than just general prime multiples? Like,
I mean, we know that the field will have characteristic that is a prime, right? So there's not much choice.
No, but you could make m is n plus a multiple of p, and then you still have that sort of, they're not the same in that they're the same.
Yeah, and I guess the answer to this would be that you would just pick the lower bound for Nullstellensatz will work for p to the d. I don't know off the top of my head if you would have more than that. I think I would just restrict away all of the other pigeons and just get p to the d ones. Like we basically, I think the lower bound operates with this quantity.
But like the largest power that defines the number of extra pigeons, or
yeah, but I don't know. You'd have to look at whether you can take. Yeah, you can probably. Yeah, what you would probably do is you'll just basically you'll pick the largest power, and then you map all other pigeons, and now n shrinks a little bit, but not too much, and then you can prove a lower bound in Nullstellensatz. I think like I cannot, if you give me 2 times p to the d, I don't think I can leverage that too.
But it's at least, it doesn't get easier.
It doesn't get easier than taking that factor 2 from the number of pigeons. I mean, I will restrict them away and get a slightly smaller influence. But the point is, like, we don't have anything for, like, you know, if you can do anything for anything like this for polynomial calculus, then great, do it. Also, I should say this, and even for Nullstellensatz, we don't know how to do this for expander graphs. This only works for complete graphs. So even for Nullstellensatz, if I give you an excellent expander with this many vertices on the left and this many vertices on the right, I think we also don't know how to do it. Now somehow this lower one, and this is okay. So I then give you, this is a Beam and Rees paper from, let me cheat, 98. So this is a fairly old paper. It's a beautiful construction, but somehow, yeah, this is worth looking into. And then the final open problem I want to mention is perfect matching on non-bipartite graphs. So there's a paper by Per Austrin and Kilian Risse from 2022 that says basically if you have a random D-regular graph, non-bipartite, and you say that it's odd number of vertices. Well, the lower bound holds for any number of vertices, but odd number of vertices is kind of the fun case, because that means that there is definitely not a perfect matching. So they get a perfect matching degree lower bound, big omega of n over log n. Okay, for fields of characteristic different from 2. Now there are two problems with this. One is like it's slightly annoying to lose this log n factor. It shouldn't be there. And the second problem is that this d has to be like humongous.
But constant.
But constant. But it's like, I mean, this should be true for, you know, I mean, yeah, some small d, right? Like d 3, 4, 5, something like this. And I don't know. I mean, it's a large number. I don't know if it's like a gazillion, but it's, I think it's like probably a. We'd have to ask Kilian Risse, but I think like a 3 or 4 digit number or something. And the reason why they do this, they actually embed this whole problem. This is also by reduction. They managed to somehow embed this random regular graphs inside of Satin instances, and we just leverage the Satin lower bound. Mm. So it's really a reduction argument. I mean, but it should be possible to just attack this problem heads on. This is, I think, another interesting, excellent problem. And above all, these problems just show that we really don't, there are lacks in our knowledge of these tools. Like, if we really understood polynomial calculus, we would be able to do these lower bounds, but we're not. So there's room for increasing our understanding. So I want to end by trying to just give a little bit of an overview of what's going to happen next time. So what's going to happen next time is basically we're going to look at all polynomials. And we want to prove that the degree of refuting a set of polynomials P is strictly larger than some capital D. Okay? And the way we're going to do this is we're going to look at everything that is derivable in degree at most D. This is like the set of polynomials we want to understand. The problem is that this might be a very crazy set. Structurally, it might be hard to understand exactly how this looks. So what we're going to do is let's over-approximate it by something that is nicer. Okay? So let me describe a nice set that is guaranteed to contain all the things that is derivable in small degree. Let me then show that one is outside. Okay? This actually goes back to Razborov, who said basically that what we should try to do is the following. So we should design a linear operator on polynomials R, which has the following property. If I take a polynomial f that is one of the input polynomials, you can think of R being 0 is like the indicator of this blue region. Okay? So firstly, R should be linear. Oh, I already said that. Okay, excellent. I wrote that. R is linear. And if you take an input polynomial in F, then R says that this maps to 0. Then R says the following slightly mysterious thing. Look at any term. Suppose that we have a term where the degree of the term D is strictly smaller than D. And look at multiplication And now this is where I do variable multiplication. Basically, the idea is I have a handle on RT, but what about XT? Then we're going to prove that R of XT is the same of multiplying, first reduce T, then multiply by X, and then apply the R operator again. Okay, and now but R of 1 is not 0. Okay. If we can do this, says Razborov, then the degree of refuting P is strictly larger than D. And now here is where, if we should stick to our original definition of monomial multiplication, I don't know, I didn't have the energy to think about it. We might lose a factor 2 here, but we really don't care because we have linear lower bounds anyway. So what I want to end by doing is to just show, let's discuss why this holds, and then next time, because basically this tells us that what we're going to do, we're going to build a linear operator next time. How are we going to build this linear operator? We're going to use our graph. This is where the UVQ graph are going to help us build this R. Okay? So where is this from? This is from Razborov in 1998. So proof of this, by induction, well, if F is an axiom, so by induction, any P derivable in degree at most D satisfies that R maps P to 0. Okay? If I can prove this by induction, then it's clear that any polynomial derivation from fancy style P in degree at most D is never deriving contradiction, because contradiction under R doesn't map to 0. Right? Okay. So if F is an axiom, we're okay. This is case 1. Suppose we do linear combination. So we have Q, we have R, and now we derive alpha Q plus beta R. Well, by linearity, R of alpha Q plus beta R is just alpha times R of Q plus beta times R of R, which, I mean, this is 0, so everything is 0. Now, the slightly tricky step, or not tricky really, but it's maybe worth doing it carefully, because we're going to pull this magic, like why, maybe it's worth seeing, like, why is this the right condition to get multiplication? Okay. Okay, so suppose we're deriving x times p from p, and we know that R of p is 0. And we know also that p has degree at most d minus 1, so that xp has degree d. Okay? And now we want to argue about what this is. Okay? So now we have to say, what is p? Well, p is a sum of terms. What is a term? Again, a term was a monomial times the field element. Let me just write terms. Okay? it doesn't matter. I mean, by linearity, so when I apply R, just when any field element in front just pops up. Okay, so RXP is then going to be by linearity. Just multiply, further, like what is this? Well, this is this. Okay, now by linearity, okay, I have a typo in my notes. I see. We now get this. Right? Oh, I didn't have a typo in my notes. I'm just going to. Okay, so this is just by expanding. Oh, and I guess I multiplied in x immediately, like in one step. But I hope you're happy with this. By linearity, we get this. Now here is where I want to use my magic property. That this is R of x, R of ti. Here is where we use the property 2. Now, by linearity, staring very, very carefully at this, this is R of ti for all the ti's in P. So if I just sum all of them up, I'm actually going to get this. Okay, but now we're home, right? And in fact, what is happening here, like what is R? So this is what we're going to start to talk about next time. Like, can we think of any R that would have these properties? Like that is linear, and that has this property and this nice property. Well, this is actually capturing, like, if we ignore the degree condition, actually what we're defining here, R is the indicator for what is derivable from this set of polynomials. Yes? So actually, R is just indicating whether I'm inside the ideal generated by the polynomials or not, except for this weird condition, but let's drop it for a while. Okay. So actually, next time we're going to recap what we know by polynomial ideas. R would be just the indicator function of the polynomial ideal would be great. That would give us everything, all of the properties we want. I mean, even without this degree condition, right?
Oh, no.
Except for one slightly annoying property.
Yeah, okay.
Yeah, this is still going to be true. You know? Something had to crash. Because, well, P is an unsatisfiable set of polynomials, so in particular, one also lies in the ideal. Okay. But this kind of tells us that ideals, if we define polynomial ideals and use reduction operators modulo these ideals, then we get everything except this. So what we're going to do next time is say, well, suppose that we somehow reduce modulo a lot of P, but not too much. Okay, so different polynomials we're going to look at, okay, you want to reduce this polynomial, well, take this half of the formula and reduce modulo it. Oh, this other polynomial will reduce modulo this other half. Okay, so we're going to look very, very carefully and do honest polynomial reductions, but not modulo all of P. But we're going to reduce modulo cleverly chosen subsets. And then, if these subsets are small enough that they're satisfiable, we're never going to violate this. Now, this is unfortunately not going to be an honest reduction. I mean, we can make it linear, that's fine. We can probably take care of this, but this is going to fail. No. Except if we're doing this in a very clever way, we can make sure that it only fails when you do your verification calculations up to high degree. And polynomial calculus derivations in low degree will not be clever enough to detect our cheating. Okay, so this is what we want to do next time. So basically, we've given this set, we want to somehow pick out nice polynomials and reduce modulo those sets of polynomials. How are we going to choose them? This graph object that we defined is going to help us to cleverly pick polynomials in such a way that we can sort of stitch everything together so that it looks like the real deal in low degree. And I should say that what will happen, we'll start next lecture by doing a quick algebra recap, which you have in the notes for today also, but I think we're maybe deserve to, call it a day now and not start to do algebra. But next time we'll do a quick recap of polynomial ideals, what it means to reduce modular polynomial ideal. I'll tell you everything, but if you haven't seen it before, or if your Algebra 101 course was a while back, then maybe just check the beginning of the notes for next lecture or the very final pages in this lecture, because that will help you. Then we're just going to basically start juggling polynomial ideals and use that to prove once and for all our polynomial calculus rho ones. That's the plan for next week. So that ends today's lecture. Any questions?
Yeah.
Yes.
So these linear operators do remind me of the pseudo expectations operator for Shirley-Adams.
Absolutely.
And pseudo expectation operators kind of correspond also to pseudo distributions. So my question is, do those linear operators also kind of translate in the algebraic way to something that you could call a pseudo ideal or something?
Well, I mean, in a sense, something that behaves like this is a pseudo ideal. Like the fact that R looks exactly like it looks like you're reducing modular an ideal, because an honest reduction modular an ideal would behave exactly like this. So it seems like you're faking a reduction modulo some kind of ideal. And so it's a very good point. So again, for Shirley-Adams and sum of squares, we have these pseudo expectations. Also for Nullstellensatz, we didn't talk about that, but there are designs for Nullstellensatz when you want to prove degree lower bounds there, which are sort of baby versions of pseudo expectations. So all these Nullstellensatz, polynomial calculus, Shirley-Adams, and sum of squares, they all have these pseudo objects that fake it. They basically fake that the input is satisfiable and then give me a distribution or something. So for Shirley-Adams and SOS, I guess you can think of it as being taking expectations over some distribution over the solutions. Here, you can think of it as well, since the polynomial set is satisfiable, we just reduce modulo this set of polynomials. I mean, it's satisfiable, so clearly R1 is not zero.
Yeah.
And look at properties 1 and 2. Clearly, this is a polynomial ideal, except that let's sweep under the rug that don't let the degree go too high. But that's exactly what fails in Shirley-Adams and SOS also, right? For your pseudo expectations crash if you go to too high degree. Are there deeper connections here so that you can maybe like transfer techniques or intuition? That's a truly excellent question. I don't know that anyone has worked this out. I think it would be well worth thinking deep about this, because they are so similar. I mean, one difference is that for Nullstellensatz, Shirley-Adams, and SOS, you only need to map things to numbers. So maybe what is not so clear from this notation here, where actually R is going to map polynomials to polynomials.
Oh.
We're not going, so maybe I should have said that more clearly. This will actually, what will pop out of this are other polynomials. They're not in general numbers, except that if you're doing your polynomial calculus over the reals, then I think you could just take your pseudo expectation and it would kind of work, I think. And this is, if that is true, that's a special case of actually saying that over the reals, sum of squares is strictly stronger than polynomial calculus. Okay. But yeah, the difference is that we'll say that R will actually, it's a polynomial reduction, so it will spit out a polynomial. When you put in a polynomial and you get, in general, not a number out, but a polynomial out. Yeah, so good. I should have said this more clearly.
I have a second question
Yes.
about what you said about the dense linear ordering principle. Do we know anything about its Arbrandized version? Like when you have a function that takes two parameters and gives you something that is supposed to be in between. Do we know maybe it has a trivial upper bound, or I don't know?
No, and I don't know how you would. Okay, firstly, I'm not sure how you would formalize Herbrandization in this setting. Whether it sounds like somewhat similar to also for the dense linear order, you just as for the linear order, you sort of have the problem that you need to somehow narrow down the possible range of witnesses, because otherwise the dense linear order will also be very wide.
Yeah, for sure. Of course.
So the way to make the dense linear order less wide, you could do one of two things. Either you do the standard translation of wide clauses to 3 CNF formulas with auxiliary variables that we talked about a couple of lectures back, I think, very quickly. The other thing that you could maybe do is, again, impose an expander graph on your finite set and say that if X is smaller than Y, then there is someone in the common neighborhood of X and, there is someone in the neighborhood either of X or of Y with respect to the graph, which is smaller than both. And then you'd again get like for a D-regular graph, you now get a 2D CNF formula. And we don't know, I think it depends on who you talk to. It's like believable that it should be possible to get polynomial calculus row bounds for this, but it seems like I definitely don't know how to do it.
Because those Arbrandized versions are like made to have clauses of which polylogarithmic, right? So already maybe, I don't know if you would still need to do the graph trick since the clauses are not as wide anymore.
Yeah, I don't know. I mean, again, polylogarithmic width is fine, right? Because as long as we don't need constant width input. I mean, you only need to, because as long as that, like you have a refutation degree that is linear, and if the input is polylogarithmic, like who cares?
Yeah.
Yeah, I don't know. Maybe you can. I don't know what would happen to the lower bounds we're doing here. I guess you can Herbrandize like a lot of these formulas, maybe.
Yep.
I'm not exactly sure what the syntactic objects would look like. I'm not exactly sure what kind of lower bounds we would get.
Okay.
It's a good question. Okay, so let's call it a day.